Hey there, we're going to go over some Newton's third law notes. And what we're going to find here in Newton's third law is that forces, they always act in pairs. And so what we'll call that is force pairs. So I'll put here force pairs. And you probably remember from middle school where your teachers told you the action and reaction. There's an action and reaction force, and that's basically describing Newton's third law. And so whenever we have a force exerted on an object, there's always going to be a equal and opposite reaction force. And so let's kind of look at that and see what that looks like. So let's say, oops, we have the wall here, and I'm standing here next to it, and I decide to go ahead and start pushing against this wall. And let's say that I apply a 30 Newton force to the wall. So what that would look like in terms of forces, that means I have a force that I'm applying to the wall, and so that force on the wall is equal to 30 newtons. Now, there's never going to be a force without some kind of a reaction force. So there's always a reaction force that takes place. And in this case, that reaction force is a force exerted by the wall. And it's going to be applied to the person pushing the wall, and it's also going to equal 30 newtons here. And so your action force is you pushing the wall, and then your reaction force that's taking place is the wall pushing on the person. And if you notice, they're the same magnitude, so your reaction force will always have the same magnitude. So in this case, it was 30 newtons for your magnitude. And then they're also going to have an opposite direction. Okay, you're pushing the wall to the right, but then the wall is pushing you to the left. So your reaction force is going to be opposite the direction of the action force. So we have our action force and a reaction force. Now, one thing to make note here is that they happen simultaneously. Okay, so your action and reaction they happen simultaneously. Okay, so in other words, you don't have that the action force doesn't come before the reaction force. It happens at the same time. And so let's look at kind of an example of this and how we can apply this Newton's third law. So let's say that you're standing on a piece of ice here. And let's say you're holding a ball and a real heavy medicine ball or something. And let's say that the mass of that is equal to 10 kilograms. And let's say you have a mass of 100 kilograms. And then you throw that heavy medicine ball, and let's say after you throw it, you start to accelerate backwards at with an acceleration of 1 meter per second squared. So you throw the ball, after you throw the ball, you start sliding backwards with an acceleration of 1 meter per second squared. And so let's try to solve for the acceleration of the ball after you throw it. And so we can apply this force pair concept in Newton's third law to solve for this. So we know that Newton's second law told us that our net force is equal to the mass times the acceleration. So for you, the net force exerted on you, you have a mass of 100 kilograms, and your acceleration is 1 meter per second squared. So the net force on you was just 100 newtons. And based on this action-reaction, that means that there was 100 newtons of force applied to you by the ball, so there had to have been 100 newtons of force applied to the ball. And we can use this to now solve for the acceleration of the ball. So Newton's second law again says acceleration is equal to our net force divided by the mass. So your net force is going to be the 100 newtons, okay, because it's equal and opposite direction here. So you would have 100 newtons for the net force, and then the mass of this ball is 10 kilograms. So the acceleration of the ball here is just going to be 10 meters per second squared. Now, another thing that we're going to start looking at is what we call a system of objects. So up to this point, everything that we've seen, we've been analyzing one individual object. And so now what we're going to start seeing is a system of objects. And so all a system is, it's a collection of objects. So you got two or more objects that are within a system. Now your system, it can be determined by you, the observer. Sometimes your teacher might tell you what's involved with in the system. And then also sometimes the problem will give you those parameters that determine what makes up a system. So a system is just going to be two or more objects, a collection of objects that we're analyzing. And then the key here is that we can apply this Newton's second law not only to an individual object like we did up here, but we can also apply Newton's second law to a system of objects. Okay, so we're going to apply Newton's second law to a system. And so let's look at a few examples and kind of see what that looks like. So this one here says the system shown below consists of two identical blocks, mass 5 kilograms being pulled to the right. There's no friction, and then the tension in this T1 is equal to 30 newtons. So let's go ahead and start applying Newton's third law and Newton's second law to this system to solve for our T2 here. Okay, so we want to solve for this tension 2. So to start this out, we'll go ahead and make our free body diagrams of our two objects. So we have object 1 and object 2. Object 1, we have Fg down. We have the normal force going up. And then we have the tension T2 to the right. Now it told us there was no friction here, so we're done. Now object 2, you also have your Fg going down, your normal force going up. We have T1 to the right, and then we have T2 to the left. And so from here, we'll go ahead and make our net force equations for both of these objects. For object 1, your net force equation is just equal to T2. For object 2, you have your net force equation T1 minus T2. And so since we're looking at this as a system of objects, not just an individual object, what we can do is we can go ahead and solve for a system of equations here. And to do that, what we'll do is we'll take the net force equation for object 1. It was equal to our T2. And we have our net force equation for object 2 and is equal to T1 minus T2. And we're going to add those together. And by adding those together, if you look at the right side, you have T2 plus T1 minus T2. Well, that's going to cancel. And so on the right side, you're just going to be left with T1. And what we've done here is we've now solved for our net force of our system, object 1 and 2. Now remember, Newton's second law says that net force is equal to mass times acceleration. So what we end up with here is the mass of your system times the acceleration of your system is equal to T1. And now we can solve for the acceleration of that system. So the acceleration of your system is going to equal T1 divided by the mass of your system. And now we can plug in and solve for that acceleration. So the problem told us that our T1 was equal to 30 newtons, and the mass of each block was 5 kilograms. So you're left with 30 newtons divided by, we have 5 kilograms plus 5 kilograms. So the acceleration of your system is going to equal 30 divided by 10, which is 3 meters per second squared. Now, because these objects are connected by this string here, that means they're going to both have the same acceleration. Okay, you can kind of think of it, if you're pulling a sled and you're running down the street pulling a sled, well, that sled's not going to speed up and run into you, right? Now, unless you're on some kind of an incline or something, but if you're running horizontally, you're going to have the same acceleration because you're connected. And so now what we can do is we can um, use this acceleration to solve for our T2. And to do that, we're going to go back to our original net force equations. Now, it doesn't matter which one we use here. Either way, you would get the same answer. And I'll go ahead and show you that. But in the future, you only have to use one of those net force equations. And generally, you'd pick the one that's easier to work with. Looking at these two net force equations, I'd be able to solve for T2 faster using this one. But again, I'll show you how you would get the same answer for both here. So let's start with the one on the left. So the net force equation for object 1 is just equal to T2. We can apply Newton's second law, so the mass of object 1 times the acceleration of object 1 is equal to T2. The mass of object 1 is 5 kilograms. We just solved for the acceleration, it was 3 meters per second squared. So T2 then is just equal to 15 newtons. Now let's go ahead and solve using our other net force equation just to show that it doesn't matter which one we use, either way we'd get the same answer. So your net force for object 2 was equal to T1 minus T2. We'll substitute Newton's second law, rearrange it for T2, so we'll add T2 to the left, subtract the M2A2 to the right. So your T2 is equal to T1 minus mass of object 2 times acceleration of object 2. So now let's go ahead and just plug in our numbers. So T1 was equal to 30 newtons minus mass of object 2, 5 kilograms, acceleration of object 2, 3 meters per second squared. So you got 30 minus 15. T2 is equal to 15 newtons. So you can see either way, we got the same answer, right? 15 newtons. And so this here, T2, is just equal to 15 newtons. Now, to kind of sum up what we did when we're analyzing this system of two objects, we made our free body diagram for both objects, net force equation for both objects. Then we created our system of equations here for the system of the two objects by adding those together. Once we did that, we could solve for the acceleration of our system. And once you have your acceleration of your system, you go back to your original net force equations. You only need to pick one of these, go for the one that's a little easier to work with. So this one in this case, right? Because there's a lot less math and manipulation than this one over here. And then you can solve for that internal force, right? That force pair. Now, another example here is if we have something like this. So this one says we have a 3 kilogram block, and then it's at rest on a table. It's connected to this other block of 2 kilograms, and that string goes over a pulley here. And so we're going to solve for the tension in the string that's running over the pulley. So let's start out, let's make our free body diagrams. And so for the M1, we'll call this the M1 here. It's a 3 kilogram block. So we'll draw that down here, Fg, and that equals 30 newtons. And the normal force is going to also be 30 newtons. And then there's this tension to the right. And then for the other block, we'll make that one block 2. You have the mass is 2 kilograms, so that means your Fg will be a little bit shorter, and it's 20 newtons. You have your here going up. Now there's no normal force, but you're going to have this tension. Now let's make our net force equations here. So for the one on the left, the one that's on the table there, your net force equation is just equal to the tension. And the one on the right, you have your net force is equal to Fg minus tension. So you might be wondering, why did we do Fg minus tension instead of tension minus Fg? So when we have a situation like this, what we do is we call this our positive x direction, and then we'll call this our positive x direction. So our string is basically representing our x direction. Okay, so we're just going to shift our x and y for this M2 block. And so now, by doing that, we can actually create our system of equations here for this system. So let's add those net force equations. So you have the net force of object 1 is equal to T. Net force of object 2 is equal to Fg minus T. So the net force for your system is just going to equal Fg. And we'll put Fg2 because that's the Fg of block 2. Now we can solve for the acceleration of my system. So the mass of your system times the acceleration of your system is just equal to the weight of block 2. So the acceleration of my system equals the weight of block 2 divided by the mass of your system. Now we can plug in our numbers. And the weight of block 2 was 20 newtons. And then we had a 3 kilogram block plus a 2 kilogram block. So 20 divided by 5, your acceleration is equal to 4 meters per second squared. So now we have the acceleration of our system, and we can go in and solve for that internal force of the system, which was my tension. And looking at my two net force equations, this one is probably going to be the easier one to work with to solve for the tension faster. So let's rewrite that. We have net force of object 1 is equal to tension. We'll go ahead and substitute Newton's second law. The mass of object 1 was 3 kilograms. The acceleration of that is 4 meters per second squared. So your tension is just going to equal 12 newtons. Now again, we could solve for this by using our net force equation up here, and we would still get 12 newtons. Okay, so it doesn't matter which one of these two that we go back to, just usually go and pick the one that you can solve faster. So again, the same process. We made our free body diagrams for the two objects. We made our system of equations here by adding those together, solved for the acceleration of the system, then applied that to one of our original net force equations to solve for our internal force.